This is the lesson for section 4.1d over linear and angular speed. The substitute will give you the handout that you see here with our example, and you're welcome to write on it whatever you need. So let me point out that I am going to show you how the formula that you are going to use is generated. But the bottom line is the formula that you need to use is right here at the bottom, which is V equals R times W. But I want to show you how it's derived first. So we're going to go way up to the top and remind you of the fact that there are two formulas we know. The first on the right is S equals R theta, and that is the arc length of a circular arc. And we learned that S, the arc length, is equal to the radius length times the measure of the angle theta in radians. Then that actually comes from the fact that an angle in radians is theta equal to the arc length divided by the length of the radius. That's actually how an angle in radians is defined. So that's going to come into play here when we look. For the definition of linear and angular speed, it says, if a point is in motion on a circle of radius r through an angle of theta radians in time t, then its linear speed is v equals s divided by t. So v is going to be equal to, the linear speed is going to be equal to the length of the arc divided by time. And then it says where s is the arc length given by s equals r theta, so really you can see down here, v equals s over t really would become v equals r theta over t. And so then we have to understand that angular speed, which I have boxed in red, w is equal to theta over t. And so in the formula that you see right here, we have theta over t, which I circled in green, and that's really angular speed. That's the angle in radians per unit of time. And so the formula v equals s over t becomes v equals r theta over t, since s is really r theta. And then because we have theta over t, and that's really angular speed, the angle in radians per unit of time, then we're going to replace theta over t by w, and that's how we get this formula down here, that v equals r, the radius, times w, the angular speed. So let's see how this plays into an example. I'm going to slide down here, and this is really used when you have objects that are in motion in a circular path. And we can pinpoint a point on that circumference as it's going around. Think of a tire. If you run over a nail on a tire, the nail's embedded in the tire, and it's rotating around as the car moves. And so that's what we're talking about with linear and angular speed. So it says a windmill in Holland is used to generate electricity. Its blades are 12 feet in length, a lot smaller than those big windmills you see out in fields today. The blades rotate at 8 revolutions per minute. Find the linear speed in feet per minute of the tops of the blades. So when you look, of course, we know that the radius is 12 feet. To find the velocity, or the linear speed, we need to know the radius, but we also need to know the angular speed, w. And the only other number we're given is that the blades are traveling at 8 revolutions per minute. And so it's that that we use to help us find the angular speed. So if the windmill blade goes around at 8 revolutions per minute, each revolution goes through 2 pi radians because that's equivalent to 360 degrees. And so, like factor label multiplication, 8 revolutions per minute multiplied by 2 pi radians per revolution becomes 16 pi radians per minute. And that's actually what we use right here when we substitute in to calculate our linear speed. We take our radius, 12, times 16 pi radians per minute, and feet times 16 pi radians per minute gives us 192 pi feet per minute. And that's where your calculator can be used to approximate, and you should get about 603 feet per minute. So it's really the angular speed that's really going to be critical. And remember, W, the angular speed, is found, in this case, taking those revolutions per unit of time and multiplying by 2 pi radians per revolution. And that converts it to angular speed. And then at that point, you just multiply by the radius length, and you will have linear speed. All right. The only other thing I want you to understand today is how we convert from a degree that could be given in degrees, minutes, and seconds to a decimal degree. Fractional parts of degrees are measured in minutes and seconds, kind of like a clock. We have hours, minutes, and seconds. Well, we have degrees, minutes, and seconds. And a minute is 1/60th of a degree. And a second is 1/60th of a minute, which means if a minute is 1/60th of a degree, 1/60th times 1/60th means a minute is 1/3600th of a degree. So you can see here, we use the double, like the quote mark for seconds, and the single mark, like feet, as minutes. So you see here 31 degrees, 47 minutes, and 12 seconds. One way to calculate the decimal form is like this. You can take 31 for the degrees and add 47 over 60, because that's how much of a degree 47 minutes would represent, plus the 12 seconds really is over 3,600. That's how many seconds that's how many seconds in a degree. So we'd add that all together to get us that answer in degrees, which is about 31.787. Now, if you needed to convert back, you will be able to find something that looks like that. DMS means decimals or degrees, minutes, and seconds. And it can take your decimal degree and convert it back to degrees, minutes, and seconds. I'm showing you on a calculator here, if you press the blue key right here, second, and the angle key, which is above the apps button, that will bring up a menu, and you're going to see on it that there are degrees, option 1, minutes is option 2, option 3 is not seconds. Seconds is kind of weird. To get seconds, you are going to have to press, and let me change my color, the green key alpha and the plus sign that will get the quotation mark that is used for seconds. And I try to show that here. I think I have the decimal form of a degree, 25.945 degrees. If I want to go to degrees, minutes, and seconds, I choose second and the apps button, which I might have circled that wrong up above, but you get the idea. And if you press enter, then that will give you the answer, which you see here, which 25.945 degrees is 25 degrees, 56 minutes, and 42 seconds. It's the fractional part of a degree that the 0.945 represents. All right, so I hope that helps you in completing the assignment for 4.1D in My Math Lab. All right, we will see you on Block Day.